Morning. Can people hear me okay? Back? Thumbs up? Yes. Okay, great. So I'm Justin Stevens, professor of William and Mary. I'll be telling you about hadron spectroscopy. I'm going to focus not so much today, but tomorrow on an experiment called GlueX, which is the one I'm primarily involved in Hall D. So a little bit of preliminaries for how I'd like to go through the next. Can you click on the slide once to?
Right.
Okay, a little bit of preliminaries of how I'd like to go about these set of lectures today and tomorrow morning. My goal is to give you a self-contained introduction to hadron spectroscopy. I'm going to give you a bit of an overview of the excitement in both things going on here at Jefferson Lab and things going on outside. And today, that means we're going to start with some introduction to why hadron spectroscopy is interesting for QCD. A little bit about how we study spectroscopy and QCD together, and then we need some framework for how we're going to classify these different kinds of hadrons. And this will be important as we talk about the more exotic versions of hadrons that exist or maybe don't exist, and we'll talk about that some more today. So that's the plan, and then after the break, we'll talk about the so-called XYZ particles in the hadron spectrum and why they're particularly. So please stop me as you have questions along the way. Put up a hand. We have a couple of exercises this morning that I'll have you try to go through as well to make it a little interactive. So stop me if there are questions. All right, then. Let's talk about where QCD fits into the standard model. I guess you heard yesterday some more from the theory side on QCD itself and how it works. I'm going to be giving you a more qualitative picture of QCD. And so in the framework of the standard model, we know that there are these matter particles, the quarks and the leptons, and the force-carrying particles, the bosons. And for our purposes today, we're going to ignore everything except for the quarks and the gluons. So we're focusing just on QCD in the standard model. So really in this strongly coupled regime where the quarks are bound inside of the hadrons. So as opposed to some of the deep inelastic scattering you were thinking about yesterday where you could use perturbative QCD effects, we really need to focus here on in the spectroscopy side of things on the strongly coupled regime. So a little bit about why looking at the spectrum is interesting. Some of the things we know about hadrons were very informative for how we developed QCD to begin with. So a little bit of history. When people started looking at the structure of the proton, they had this model of up and down quarks. And so they put together a proton that had two up quarks and a down quark, and you can align their spins in such a way that you get the up quarks with opposite spin. And so they're okay in this antisymmetric state. And then you've got the neutrons being in up and two down quarks. You can spin a half for both and come up with the properties for the neutron and the proton this way. But then people observed in experiment that there was another resonance, another hadron that existed called the delta plus, and it had positive 2 units of charge. And it was observed to have the spin 3/2 quantum numbers. And we'll talk more about the quantum numbers later. And with that, you needed to have 3 up quarks, which all had their spin configuration pointed in the same direction. So what's the problem with that system?
Pauli exclusion principle.
Yeah, Pauli exclusion principle. So if you write down the wave function of this thing, it is symmetric in spatial, symmetric in spin, and symmetric in flavor, the type of the quark. And so how do we deal with the fact that these things has the wrong symmetry? Well, we add another component to the structure, which is the color coordinate. So we have a new quantum number, color, that allows us to have this thing still satisfy all the nice quantum statistics for fermions that we need. So this is an example of folks going and looking at the spectrum, observing that there's a hadron that has these properties of spin 3/2 and positive 2 units of charge. And it tells us that we needed this color charge as one of the degrees of freedom in what turned out to be QCD. So this color charge allows us to write down baryons that have these red, green, and blue colors. So 3 quarks inside of them, but also we can have hadrons that are made up of quark-antiquark pairs. These are called mesons, and they come in different flavors. So the conventional one you've probably heard about already is the pion that has just up and down quark flavors inside of it. If we trade out one of those down quarks for a strange quark, we can make things called kaons. And as we'll talk a little bit later today, the focus today actually will be on the charm quark systems. And so if we trade out one of those up quarks for a charm quark, we can build up the D mesons. And if you add higher mass quarks, bottom quarks, you can get E mesons that are turn out to be quite interesting for doing spectroscopy. So we have these quarks, and we can build up the different kinds of hadrons that exist in nature with this quark model. And so today we're going to talk a little bit about that quark model and how we can build up the hadrons we see. But before we get into that, I want to make some distinctions between the different kinds of QCD people talk about studying. So there is the QCD in the so-called asymptotically free limit that people are thinking about studying at the Large Hadron Collider, or even here at JLab. If you look at large Q-squared electron scattering, you're really thinking about probing individual quarks inside of the nucleon. And so if you work in this region where QCD is calculable, you need to have very high energy scales. And so things like the Higgs boson production at the LHC, you can really do the calculations at the level of thinking about gluon-gluon interactions. Whereas in the experiments I do, we're thinking about probing hadron systems that have quarks and gluons interacting inside of them, where we can't isolate the individual degrees of freedom in the system. So there's this high energy short distance limit of the interactions in QCD. And then there is this low energy long distance limit. And I think you saw a plot like this one yesterday of the coupling of the strong force as a function of this Q, the interaction scale. And so when you're thinking about studying high Q-squared electron scattering at Jefferson Lab or producing some heavy particle at the LHC, you're way up here at this high Q region or the short distance limit. But when we think about interactions at the low energy or long distance limit, that's what we're primarily talking about in terms of confined quarks inside of hadrons. So here QCD is not calculable perturbatively. People use numerical techniques to try to study QCD, so-called lattice QCD, that I'll mention a little bit later. And I think you'll hear some specific talks on later at summer school. But this is an opportunity to really study QCD in a very different range than people do at say, high energy colliders or in the more weakly coupled asymptotically free region. So my talk will focus on these interactions on the confined quarks. And so you're going to hear, I think, quite a bit at the summer school about investigating the structure of the proton, thinking about it not just as these 3 quarks inside of a system. This is kind of the cartoon picture of have these 3 so-called valence quarks inside of the proton. You can make up their structure with these red, green, and blue up, up, down quark objects that we talked about. There's all kinds of interesting structure that goes on if you start thinking about probing at different distance scales inside of the proton, these quark-antiquark pairs that pop in and out of existence, gluonic structure inside of that. My talk will not talk about any of this interesting stuff over here, but we're going to be thinking about how can we build up different kinds of hadrons, not just protons and neutrons, but other maybe exotic flavors of these guys, and not really dealing with the internal structure of those. Okay, so you'll hear more about this stuff from Ming and others, I think, in terms of proton structure or nucleon structure later. So a little bit about why it's interesting to study QCD. If we're in this strongly coupled regime, the gluonic self-interactions function quite differently than they do in maybe something you're more familiar with in electricity magnetism or QED. There we just have this one photon coupling to if we're dealing just with quarks, the quark-antiquark vertex here. And there you have the fact that with that one coupling, as you go to larger and larger distance scales, the force or the potential falls off as you go to large values of R, the distance between a couple of quarks. The quite interesting thing about this gluonic interaction is that it has a self-coupling. So you get these 3-gluon or 4-gluon interactions. And so the gluons can couple to themselves. And what that leads to is the force or the potential growing linearly with distance. So as you think about these hadrons, if you were to stretch this quark-antiquark system farther and farther apart, you're actually gaining energy as you're stretching it farther and farther apart. It takes more and more energy to pull it apart. And so that's this confined study of the quarks inside of the hadrons. So the gluonic field itself is quite interesting. And what we'll talk about a little bit more tomorrow are the potential for having unique gluonic configurations that hold together the quarks inside of some of these hadrons. Yeah.
If it just continuously grows with distance, the potential, then why doesn't everything implode ground force?
Yeah, great question. So I think the question is, if I stretch these two quarks apart and that takes more and more energy, why doesn't it just suck back into itself? Yeah. So there are effects like the Coulomb barrier that prevent you from getting too close together. But also, if I stretch these things far enough apart, eventually it becomes energetically favorable to just make two new hadrons. And so you can think of it really like a, I don't know if I have a cartoon here, but if I have my quark-antiquark system, and I stretch them farther and farther apart, eventually you're going to make a Q bar and another Q bar. And so that picture of like popping a new Q bar out of the vacuum allows you to stretch these things far enough apart that it's actually cheaper energetically to make two hadrons than one.
Okay, so the reason why like all matter doesn't just like implode on itself is because it's more energetically favorable for, you know, it to remain as separate hadrons, basically.
That's right. Yeah, we benefit from having the ability to produce new pairs of quark-antiquark pairs, if you like. Okay, good question. Other questions? All right, keep them coming, and we'll keep working through it. So how do we think of building up these states of quarks and gluons? Well, as I mentioned before, we're going to work in these kind of cartoonish pictures of just simple quark-antiquark systems or 3-quark systems, either mesons or baryons. And we've observed a lot of them. So there's a whole spectrum of mesons and baryons, and we're going to take a look in the particle data group a little bit later for you to find some of those for yourselves. But we also have ways to calculate the spectrum of those hadrons from first principles QCD. So we're going to look at a bunch of plots that look like this one, where I'm going to have the mass of one of these hadrons versus the other axis will be the quantum numbers of the system. And we'll talk a little bit more about those quantum numbers in a minute. But if you look at the spectrum, we sort of have a tower of increasing masses. Over here are a few of these, the mesons. So these are the pion and kaon that I mentioned earlier with a mass of a few hundred MeV, mega electron volts. And as we go higher and higher, we get some more massive vector mesons we'll talk about later. And these are the spectrum of baryons that exist. And in black are the experimental measurements of the mass values for those different hadrons. And we'll talk a little bit later about what the width of those hadrons are. But the predictions in red are from a lattice QCD simulation of those quark and gluon interactions on a lattice, a spatial and time lattice. That discretize space and time and basically do numerical solutions or calculate numerical solutions to QCD. And they overlap really well in these really sort of standard candle kinds of hadrons. But these aren't the only kinds of hadrons that are allowed in QCD. And in fact, one of the early folks that, or Gelman was one of the early folks that came up with this quark model picture. And in one of his very early papers, he already said that we could be thinking of baryons not as just these 3 quark systems, but what if you had 3 quarks and then an extra quark antiquark? Or what if you had a quark antiquark for a meson, and then you added another quark antiquark pair? So you could have, say, 5 quark or pentaquark type objects. They obey all the properties that you need in terms of this color symmetry to still satisfy the Fermi statistics. But you can build them up with more and more of these quark combinations. Now, what we see in nature is primarily these guys, the mesons and baryons, but we'd like to probe and figure out why QCD either does allow for these things or doesn't allow for them. And so what I'm going to be showing you today are some examples of candidates for these more exotic configurations of quarks and gluons. And so some of them we'll refer to as a tetraquark, so objects that require 4 quarks in their configuration, and so-called pentaquarks, so 5 quark type objects. So I'm going to show you some examples why we think they may be real QCD resonances, maybe in some cases why we think there's some other artifact of what's going on in the interaction. But this is one of them from an experiment called BELL in Japan, where they collide electrons and positrons. They make these heavy mesons with bottom quarks in them, and then they watch them decay. And one of the ways they decay is to a so-called J-side particle and 2 pions. And the traditional spectroscopy measurements really allow you to just measure the mass of the particles produced in the system, plot a histogram of it, and if you see a bump, there's a particle. Now that's a little naive, and so we're going to talk about why that doesn't work exactly. But the spectroscopy is really looking for a, sort of like people would look for lines in emission spectra of atoms. You could look at the spectrum and see what the energy levels are. And this is an indication of some structure in the system we'd like to look at. So I'll talk more about this a little later, but just as an example of the kind of data we're going to be thinking about. Okay, so the primary focus of what I'll be talking about are the different kinds of exotic hadrons that can be produced by QCD and how do we understand them. The basic premise is that there are some hadrons that are very well described by this simple meson and baryon picture, and others that just aren't. And so they can go under a few different kinds of cases that I'll show you, and then we'll talk about some examples a little later. So some of them are just extra. They're so-called supernumerary states, meaning that our prediction for the traditional meson system expects there to be 5 or 6, and we see 10. And so we have to come up with a way for describing those, either by improving our quark model or coming up for new reasons why there could be these tetraquark or pentaquark states. Others have other requirements that make them have 4 or 5 quarks in them. Maybe they are known to have some heavy charm quark inside of them, or heavy bottom quark inside of them. And so that requires them to have charge and have some heavy quark object. And so that means they need to be something like a tetraquark or a pentaquark. One other one that I'm primarily excited about are quantum numbers that are not allowed for mesons that are a quark antiquark system. And those go by the name of a so-called hybrid meson. And we're going to talk more about those tomorrow. But these guys turn out they can have excited gluonic fields in their configuration, and those can give us new properties for the mesons. And some of them are really exotic quantum numbers we can't make from a traditional quark antiquark system. And so I'll tell you more about those and how we try to produce them in the experiment I work on, which is called GlueX, the gluonic excitation experiment, where we're really going after finding these hybrid mesons. All right, so today, what I'd like to introduce you to is how we can classify things that may make up these exotic hadrons or potentially exotic hadrons, and then try to convince you that we have some evidence for these things in the data that we look at. All right. So what is the experimental strategy before we talk about those classifications? We're going to look at data like this and also a lot more, more complicated analyses. We're going to search for new hadrons, meaning we're going to look for new particles that exist as described by QCD. And that's going to look like bumps in the mass spectrum that look like this. Also, we can look at how particles decay. If they decay in a unique way for the system that's produced, we can actually identify things like their quantum numbers, or maybe talk about the path that they decay through. So this happens to be a particle. When we don't know what a particle is, we call it X. And so there's lots of particles called X and Y and Z. And this one called X was found to decay to J psi and 2 pions. What if it was observed also to decay to some other set of particles? Would that tell us something about its nature and how it's composed of quarks? So we're looking for these bumps in the spectra, unique angular distributions, and also we want to measure things like what is the mass of this particle? So we want to look at the spectrum that's observed, how does it decay, and what are the quantum numbers, which I'm going to talk about in a minute. And really the goal of Hadron Spectroscopy is not to measure, some of the experiments you're going to hear about at Jefferson Lab are really to measure like one number really precisely. Who's familiar with the molar experiment? Yeah, okay. You want to measure something extremely precisely with a unique device that can only one in the world that can do that. And that's really important. Spectroscopy is not that. We're not after finding one thing and measuring it really precisely. We're looking for patterns. We want to measure many different hadrons and then try to understand where they come from QCD. And so these are complementary kinds of techniques. Is real value in measuring one thing really precisely. But spectroscopy is really a global effort that requires many of different experiments to look for patterns in the spectrum. So I'll try to give you some examples of that. Okay. So here's where we're going to jump into some audience participation section. So let's go back to this picture of we have a meson that has a quark and an anti-quark inside of it. We want to describe it in terms of its properties, like what mass does it have, what's its electric charge, what are the flavors of the quarks that are inside of it. And it turns out that we can describe most of that in terms of the quantum numbers of the system. So if I have two quarks, they both are fermions, so they both have spin 1/2. And I can describe their total angular momentum in terms of the total spin state of that pair, and also the angular momentum between the quark and the anti-quark system. So that J is the total angular momentum coming from the L and S of the orbital and spin components. And once I have the L and S values, I can think of a couple of other quantum numbers that tell me about the properties of the system. One of them is the parity symmetry. So if I invert the spatial coordinates, then I do a couple of things. The quark and the anti-quark have, the quark has a positive parity and the anti-quark has a negative parity. So I get one factor of -1. So this -1 to the 1 from that. But also the L, the angular momentum, is described by something like the spherical harmonic. And if I change invert the spatial coordinates, then I get a factor of -1 to the L from that. And so in terms of the parity of this system, it's described by this -1 to the L plus 1 quantum number. And the other the quantum number we're interested in is the charge conjugation. So if I change particles to antiparticles, it turns out that a -1 to the L plus 1 is the factor that I get for that. So what I'd like you to do for the next couple of minutes is to think through, given different values of L and S, what the kinds of combinations of quantum numbers I can come up with that would be allowed for a system of a quark and an anti-quark. So you might just start with L equals 0 and S equals 0. What if I have no angular momentum and these things are anti-aligned in their spin? What's the quantum numbers, JPC, you can come up with for that? And try to work out a list of some allowed quantum numbers for this quark anti-quark system. So take a minute, think about it, ask me questions, and we'll come back and try to write some on the board of what people come up with. Okay, so what are some allowed sets of quantum numbers? Spin, total angular momentum, J, parity, and charge conjugation people come up with. Yeah,
Simple case, if you take L equals 0, S equals 0. 0 minus 1.
yeah. So L equals 0, you get a minus for that opposite parity of the two quark and antiquark. S equals 0 and L equals 0 together. Charge parity plus parity, or charge conjugation plus parity minus 0 minus plus. These are the so-called pseudoscalar mesons. Okay, any others?
If L is equal to 1 and S equal to 0.
Let's use the mic so everyone can hear.
Okay.
Sure, yeah. So you have L equals to 1, S equals to 0, so you get 1 plus minus.
1 plus minus, okay. These are the pseudo vectors or the axial vectors. Any others? Say again?
L equals 0, S equals
L equals 0, S equal 1. Okay, what do we get for that?
1 plus.
Sorry?
I think 1 plus.
Well, so we get L equals 0, so we're gonna get a minus sign for parity. And L equals 1, we'll get a minus sign or sorry, S equal 1 gives a minus sign for charge parity. So that's a 1 minus minus, the so-called vector mesons.
If you had L equals 1, S equals 1, you would have a 2 minus plus.
2 minus plus. Okay, so we can start to build up a pattern where we get different sets of quantum numbers. We can see things like these even ones have a minus plus with them. That looks okay. The odd ones can have minus minus or plus minus. It turns out there's going to be some that actually are forbidden, quantum numbers that we can't get out of this system. So a set of forbidden ones that aren't allowed. Turns out the lowest one is 1 minus plus. Or sorry, there's a 0 minus minus that comes first. But and on up. So there are a set of allowed quantum numbers, and we can actually describe those pretty well. And what I'd like to do is talk about some of those. But there are also some that we just can't make with this traditional or conventional quark antiquark system. And so what I'd like for you to do in our first, can you click on the slide maybe one more time? In our first exercise is to go look up some of these particles that have these quantum numbers. So in the field, we use this thing called the particle data group as sort of the encyclopedia of the hadrons we see in nature. Who's used the particle data group PDG webpage before? Excellent. So there's lots of good stuff on there. There are reviews of how experiments work, reviews of theoretical concepts. But one of the primary places we use it in spectroscopy, let's see, can I click on that the link?
This is more.
One of the primary things we use it for in spectroscopy is this interactive listings of particles. So if you click on this PDG Live, you'll get the picture that I showed you on the previous screen and the slides. And this one down here called Light Unflavored is going to have a big long list of all the kinds of hadrons that we see in the spectrum. So I'd like for you to go look through here, find an example of a couple of these allowed JPCs, and then look at the properties, for example, of the forbidden ones, and see if you can find one that has quantum numbers that don't abide by our conventional quark anti-quark system. So take a minute, browse through some of these entries. You can find things like the pion, one of these axial vectors. The nomenclature here is a little different than what I wrote on the board. JPC are the ones in the parentheses. These first quantum numbers out here are the so-called isospin and G parity quantum numbers. So focus on these ones inside the parentheses and just look through those for a couple minutes and we'll talk about them. Yeah.
Let's use the mic so everyone can hear. Yeah.
L equal to 1, S equal to 1 is 2 plus plus.
Yes. We can get L equal 1, S equal 1. Yeah, 2 plus plus. So I'll try to write down some of the terminology we use for these. We have, this is the vector. This 2 plus plus is called a tensor. And the 2 minus plus is a pseudo tensor or axial, yeah, pseudo tensor.
Sigma.
And there are more of these, right? You can keep going up with higher L and higher S to get spin 3, spin 4, all kinds of higher order systems.
How do you know that whether it is a pseudo vector or?
This shout, it's really inaudible.
So how do we know that whether it is a pseudo vector or vector?
So how do we know whether the particle looks like this 1 plus minus or 1 minus minus? Yeah, great question. We're not going to learn that from the mass. We're not going to learn it from the width, but we can learn it from how the particle decays. So with these quantum numbers, the way they behave, the spin and parity especially are going to tell us about how they decay, and we can look at their angular distributions when they decay. So think like the hydrogen atom. You can look at different L and M quantum number states of the hydrogen atom. We can do the exact same thing with the hadrons, and we'll talk about that some tomorrow. Other ways of thinking about it, you can look at how particles decay, what particles they decay to. If you have a particle that's a vector meson, it is allowed to decay to 2 pseudoscalars. So if you watch a row meson decay to 2 pseudoscalars, 2 pions, it has to have the properties that the parity and charge conjugation that you started with match the parity and charge conjugation of the particles they decay to. And so there are allowed decays and not allowed decays to satisfy those symmetries.
So for pentaquarks, what you suggested earlier, like experimentally for pentaquarks, is there any violation for parity?
No violation for parity, but it turns out we don't actually have a great way of measuring what the quantum numbers of the pentaquarks are. It's actually challenging to determine that. And we'll talk about that a little bit after the break this morning. Yeah, question.
If 0
Wait
corresponds,
for the mic.
if the 0 ones are called scalars, the 1s are vectors and the 2 are tensors, what do they call the 3s and 4s, whatnot?
We run out of names when we get up there. Yeah, I don't think we have a great name for spin 3. Yeah, I don't think it's been 3.
Should have called them matrix so you can save tensor/3.
I mean, so let's go up and maybe look at the PDG, because that's a little more interesting. So what have you found here? These J's continue increasing. And we're going to talk about some of these lightest particles because they're really well known and we've studied them a lot. But there are lots of particles listed in here where the subscript is the spin. So you can see the I sub 2 is a 2 minus plus. And there are things all the way up to, I think there's 4s in here somewhere. You have to go to pretty high mass. Yeah, so somebody claims that they measured an F6. So that's a J equals 6 plus plus wave. Now, all these come with a little bit of a grain of salt. Experimentalists go measure something, and then they tell this committee on the particle data group, here's what we measured, and they try to decide how well the experimentalists measured it. And in some cases, they even give a number of stars, like a Michelin star rating for the particles you've observed, how well they've been observed, how well they're known. And so you can look at one of these individual entries. Let's click on this one. There is one measurement that has claimed they observed this thing to decay. It has this mass and this width, and it decays to 2 pions. But there's no other confirmation of that from another measurement. Whereas many of the other particles that you'll see listed here will have lots of decays measured. Let's go look at one. Oh, what's a good one? Let's look at omega. We'll talk about that a little bit in a minute. So the omega has been measured in a bunch of different decay modes. We use it even experimentally to understand how our detectors work. It's so well measured, we can actually calibrate our detectors using a signal like this one. And it's measured to decay a bunch of different ways, some of them with really low probability. So this column over here tells you about the fraction of the time that this hadron decays to, in this case, an electron and a positron. That's 1 in 10 to the minus 5 of those decays happens that way. But there are other really probable decays, like it decays to 3 pions quite often. And so you can use the fact that we know it's a vector meson and see that it decays to 3 pions, which are pseudoscalars, and you can figure out that that's an allowed decay. But there may be some others that are not allowed, given the quantum numbers of the system. Okay. Other questions about this? You will find any of the forbidden or exotic quantum numbers?
Yes, the pi 1 1600 is 1 minus plus, which is forbidden.
So this pi 1 1600 is one of the golden things to go look for. It has exotic quantum numbers, so it can't be made up of just a quark-antiquark system. And there are good reasons from calculations from lattice QCD to indicate that this pi 1 1600 is actually a so-called hybrid meson. So it has not just a quark and antiquark, but an excited gluonic field in its configuration. And with that, it tells us something new about QCD. And so one of the things that spectroscopy experimentalists like me and also our theoretical colleagues are trying to do is look for if there's a pattern of these exotic guys, and not just the pi 1 1600, but others that have exotic quantum numbers. And there's some more listed in the table that have exotic quantum numbers as well. Yeah, question? Or, okay, good. So the particle data group page is your friend. Go look up your family of hadrons there, and yeah, come ask me questions about it. Am I moving around too much up here?
What you want.
Okay. I see. Okay. All right. So we have these conventional quantum numbers and the exotic quantum numbers. How do we classify mesons then? So in the particle data group, the mesons that are listed under this quantum number 0 minus plus, the pseudoscalars that we wrote down over here, turns out you can group them in terms of particles that have the same properties. So these are the lightest spin 0 mesons, the so-called pseudoscalars, and the pi 0, the eta, and the eta prime are all electrically neutral, and they have 0 net strangeness. So they live on this line of 0 strangeness and 0 electric charge. And there are other members. There are charged pions that have non-zero electric charge. Those are these other two diagonals. But they also don't have strange quarks in them. So everything here is net, just up and down quarks. And then on the corners, we get these 4 guys, which are the kaons that add a strange quark to the configuration. So these are called nonets of mesons. They're groups of 9 mesons that have the same quantum numbers, JPC, but different quark flavors. And it turns out we can build up more groups of these guys. The next lightest one is the 1 minus minus, those vector mesons. And those have a similar pattern. The pions get replaced by these things called the rho, and they're now K stars, excited versions of the kaons that still have strange quarks but have higher masses and have a different spin. And so what we're looking for is patterns of these hadrons that we can describe both experimentally and theoretically. Okay, so these are a list of those allowed quantum numbers we were looking out. It turns out that, as I was mentioning before, lattice QCD, these numerical simulations of QCD interactions on a finite spaced grid also can make predictions for the spectrum of these mesons, and they can make predictions for what fraction of those mesons should be in different flavor configurations, how they're composed of the different kinds of quarks. And so this is a prediction from our friends in the Hadron Spectrum collaboration. It's a little bit dated now, but it's still one of the shining features of the theoretical predictions of the meson spectrum. And it predicts the pion, eta, and eta prime. Once you put in a fixed value for the quark masses, which give you a fixed pion mass, then you can get a spectrum of the mesons that are predicted. And it turns out they line up pretty well with what we know experimentally. The pion is this mixture of up and down. The omega is also a mixture of up and down. And there's a set of mesons which are so-called the strangeonium sector. They have strange anti-strange configurations. This will become important because what we're going to talk about later this morning are the charm anti-charm systems, so-called charmonium region. And they'll look a lot like this kind of a system of the phi meson. So I think you'll hear more about the lattice QCD calculations from Kostas. But just know that there is a strong theoretical backing that's telling us about the spectrum of mesons coming from QCD first principles. They tell us really well what's happening down here. When they get up to the higher masses, that's where things become a little more shaky and where we need experimental studies, and also finding if these patterns predicted by lattice QCD match up with what we see experimentally. So that's one of the things we're after from the experimental side. Okay, so how do we go measure these things? As I mentioned before, we need a global picture or global set of experiments to try to study them in different ways. So we can find these patterns of hadrons. And I'm going to try to group those in terms of experiments in different, the kinds of systems that they study, whether they're studying heavy quarks, the charm and bottom quark systems, or they're studying light quarks, the up, down, and strange systems. And then in terms of the probes that they use. So there are mostly electromagnetic probes. So we use photon beams and electron beams at Jefferson Lab. So this is where our most of the work exists here. But there are experiments that use electron-positron annihilation to study the production and decay of mesons and baryons. And I'll talk about a class of those a little later today. And then there are hadronic probes, so often using either a beam of pions or some proton-proton, proton-antiproton collisions to produce hadrons from a quite messy initial state, but then can look at quite rare decays of baryons there, or mesons and baryons there. So we'll talk about, especially the LHCb experiment is quite prolific in this area in our field. So I'm going to focus, tell you a little bit about these guys, which we'll spend most of our time tomorrow talking about, and then come back to the heavy quarks, which is what the rest of this morning we'll be talking about. So in the light quark system, we use the CLASS and GlueX experiments at Jefferson Lab. You're probably going to hear about these and maybe even see them on a tour, but I'll give you a brief rundown. Here we have an 11 GeV electron beam that goes to Hall B. There they can use linearly polarized photons. So the electron scatters at some very small angle, but if you measure the orientation of the scattered electron, you can actually get a polarization of the photon beam that's useful for studying the production of the mesons. And so they have this huge spectrometer to look at all the products that are produced in that collision. The one I'll tell you a little more about, because I'm mostly involved in it, is GlueX, which is in Hall D. And when Jefferson Lab was upgraded to a 12 GeV electron beam, this was a brand new experiment. That's now been about 10 years ago, but it is a large acceptance spectrometer. It turns out here we have a real photon beam. So you take the electron beam from CBAF in all its pristine glory, and you slam it into a diamond wafer. And when you do that, you produce Bremsstrahlung photons. And those photons travel down a pin pipe where the GlueX detector sits, and there you smash those photons into a target of liquid hydrogen and look at all the kinds of reactions that come out. So we'll talk more about that and the kinds of measurements we might want to make. But back to the question about how you study the quantum numbers of the system, you basically need a large acceptance detector so you can look at where those particles go and investigate the decay distributions that the particles have in the detector. And that's going to tell us about what kind of quantum numbers we're producing in the experiment. Another experiment that I'll mention a little bit more tomorrow is a pion beam experiment. So this one's at CERN. It's called COMPASS. And there they have a very long spectrometer because the pion beam is quite high energy, almost 200 GeV in energy. And there, when you collide the pion with a proton target, you produce a spray of particles down here. And in that production, you can make lots of these particles X, different particles X that decay in different patterns. And one example of a spectrum you would get from an experiment like that one is these broad overlapping humps. So one of the examples I showed you earlier was this very bright, sharp feature that almost looked like a delta function in the mass distribution that said there must be a particle there that we've observed. It turns out in the light quark spectrum, where things look a lot lumpier. We wind up getting these kind of broad overlapping states. And so we have to work pretty hard to separate those out. And what I'm going to have you spend a minute or two in the next session talking about is how we can study those hadron resonances. So it turns out they have quite broad overlapping features, and we can describe those in terms of things called Bright-Vigners, and those allow us to think about the interference between different resonances. So we're going to come back to that after the break, I think. But briefly, I'll mention also these other experiments that we'll be talking about after the coffee break. When we want to study heavy quarks, we need higher energy because those charm and bottom quarks are more massive. So we need our beams to be higher energy. A couple of examples of where you can do that. You can go to the BESS-3 experiment in Beijing, and there they have electron positrons that they collide and essentially just have a factory producing charmonium systems. So they make charm-anti-charm hadrons prolifically. Well, I'll talk a little more about it later. So they do that, and it's a quite clean environment. So when you collide these two, they annihilate and produce hadrons. And so you get pictures like this where you just have, say, 3 or 4 tracks, charged particles in the event, and you can measure things very precisely. It turns out, though, that in those, look for those exotic charmonium systems, they tend to be a little more limited statistically. The other place that you can produce lots of these heavy meson and baryon systems is at the Large Hadron Collider. So rather than using some exclusive reaction like you see over here, there they smash together two protons and who knows what happens. But every so often, you can tag the fact that you measured a bottom meson, a B meson, or a lambda B, a bottom baryon. And when you do that, you get this spray in the detector, but you can measure many of those bottomonium systems, and that allows us to look for really rare processes. And it turns out LHCb is where this pentaquark object was observed and has generated a lot of interest. So it's very high rate, but it's quite messy. These proton collisions have lots of other remnants in the production that make it hard to disentangle what's going on. So we're going to spend some time talking about results from these experiments later this morning. So I think I'll pause there and take some questions, and then we can do a coffee break. Any questions from the morning session?
Yeah, could you go back to that, like? Sure, yeah, could you go back? So that, like, yeah, the sort of like lumpier invariant mass distribution.
Yeah.
So we have like only a like 12 GeV electron beam.
Mhm.
I see like you can get like a row 3 signal all the way out at like 1.7 GeV. So how does that work? How do you produce like row 3s while still maintaining conservation of energy?
Yeah, so this system, this is from the COMPASS experiment. So they have a 190 GeV pion beam.
Sorry.
So they've got plenty of energy, but it turns out we can do the same thing here. So at JLab, we can study things with masses up to around 3 GeV or so. So how do you talk about that, or how do you think about that, that reaction? So if we want to think about it in terms of the center of mass energy of your collision system, if I've got, say, photon colliding with a proton in the S channel and makes something, I don't really care what it is at the moment, I can add the momentum of my photon beam and the momentum of my proton target and take the square of that and compute the S. And the square root of S is basically the energy that you can get to in this, the mass of the system you produce. And so it turns out that if you put in a proton at rest, so the mass of the proton is 138 MeV, and a photon beam that goes up to 12 eV. If you compute that S, the maximum energy you can get up to is producing a meson that has a mass of about 3 GeV. So in terms of the mass reach of GlueX or class 12 or things at Jefferson Lab currently, the maximum mass is about 3 GeV. And as we're going to see a little later, it turns out the mass of the particle known as the J psi is about 3 GeV, 3.1. And so we can just barely make J sizes at JLab, but you can't really go higher than that. And so that means we can't look at a lot of these XYZ states at JLab right now because we just don't have the energy in our 12 GeV electron beam to get there. Other questions? Given some approximate sign here because there's lots of approximations if you want.
So this is mostly like, so we have a width in these distributions, right?
Hmm.
And there's also like the detector acceptance.
Yeah.
How do we differentiate between like what's the theoretical or something like a width there and?
Yeah, great question. We're going to talk about it after the break in the next exercise, but the short answer is when we go to describe this hadron resonance, we can do it in terms of this complex function called a Bright-Wigner. And if we had a perfect detector with no resolution effects, the thing we would measure directly is this width, gamma. Of course, our detector has some smearing to it, and so we actually measure something a bit broader. And so we have to do a fit that combines both our knowledge of the resolution of the detector and this width. It turns out that in light quark physics, like things we do at Jefferson Lab primarily, these things are so lumpy that the detector is much better in resolution than the natural width of the particles. But if you want to look for something extremely narrow, like if I go all the way back to this guy, your detector resolution might be worse than what the natural width of the particle is. So you need to account for that. And there's the function that's commonly used is called a Voitian. It's a convolution of a Gaussian for the resolution of the detector and a Breit-Wigner for the natural width of the particle. And when you do a fit that combines both of those, you can actually build in your knowledge of the resolution of the detector and then measure maybe more directly the actual width of the particle. Yeah, but we're going to play with Breit-Wigners in a Jupyter-like notebook after the break. So that'll be what's here.
Okay, perfect. It's time for a break. We will play 15 minutes.